You're welcome also from my side. So my name is Richard Föcke. I'm working for the Rosen Group in Lingen, Germany as a head of NET applications. And I will talk you today through the presentation of ultra high resolution and tank bottom inspections and an AI and machine learning use case. So as you probably all know, the bottom of a tank is a very important part of the integrity management of an above ground storage tank. Actually here, the highest risk of corrosion occurs, and most tank failures originate at the floor due to undetected or underestimated metal loss. Actually, it's quite difficult to monitor the status and the condition of a tank bottom from the outside, and therefore still a lot of tanks are emptied for inspection, and this inspection data is actually used as primary input to API 653 calculation, and therewith remaining wall thickness and corrosion rates from the bottom drive the next inspection dates typically. Actually, risk-based inspection hinges also on bottom data, so more accurate detection and sizing allow for a safe extension of intervals and optimized maintenance planning. In this screen, you see an example of how extending inspection intervals through the RBI process is possible. Actually, the wall thickness here displayed with the gray and the blue area is designed during the construction phase and the design phase with a certain degradation allowance. So we allow the wall thickness to degrade. However, we also plan in a typical safety margin and a failure zone displayed here with the gray area to always assure that the tank is not leaking. To determine a next inspection date, you have to calculate a degradation rate, and there inspections come into play. And as better your inspection data, as higher quality, as more accurate the inspection data is, as more accurate you can also calculate a degradation rate, and as more accurate you can calculate the next inspection date. So in the end, more accurate measurements lead to an extended asset lifetime, a lower probability of failure, and a reduced risks, and also in the end, optimize the RBI. Let's have a look a little bit at the industry problems and our responses to it. So the first problem of an asset owner or an operator is typically the early detection of corrosion and degradation. Of course, we want to know as early as possible if there's corrosion present and how it progresses. So therefore, the solution is to reduce the reporting threshold from 20% to 10%. In the pipeline business, this has been done even down to 5% already. The second problem is the optimization of the maintenance schedules. Of course, in maintenance and inspection, there's a lot of efforts and also preparation involved to emptying the tank, cleaning the tank, gas freeing, and so on and so forth. So you, of course, want to optimize it. And therefore, we have to come and shift to a calculated inspection interval rather than a fixed interval. And also the risk-based planning should be taken into account. The third problem is actually the improved safety, and there not only the safe operation of the asset, but also the safety of our personnel. So with an improved POD and accuracy without the need to do manual checkups, we reduce the time for our personnel in confined space. And there, of course, the automation comes into play. The last or the fourth problem actually is improving cost efficiency. Of course, nobody wants to spend more money than necessary, but we also don't want to suffer on the quality side. So therefore, it is important to identify and define proper repair criteria, which are calculated and are based on actual degradation rates. So don't use standard values. And to get to a fast turnaround time, with automation, we assure that feature lists are available on the fly and available before we leave the tank after scanning. So let's have a look how the technology evolved over time in the tank bottom inspection business. Actually, in the 1990s, the first time MFL was used in tank inspections. However, there the focus was on detection of metal loss, and we only used analog sensors, and readout was mainly done manually still. In the 2000s, the sensing technology advanced. So we used improved MFL sensors and digitized data analysis. In the 2010s, the detection capabilities have been improved, and the first time integrated multi-channel analysis has been applied. So there we did not only look at MFL sensors, for example, but also eddy current sensors came into play and data was combined. In 2015, the first automation, so to say, started, and we got to an automated feature detection and sizing. And there also the first algorithms for automation inside the evaluation process have been developed. And this basically because the sensitivity increased, the amount of features increased, and the need for automation was there. Nowadays, with an ultra-high resolution MFL tool, we even have more data. We even find smaller defects. And there, the need for AI and machine learning approaches arose to get to a fully automated and consistent data evaluation, because manually it's just not possible anymore. And this all leads to, in the future, probably predictive maintenance. So we aim for being able in the future to predict a status or condition of a tank before we even have to open it up. So what does ultra-high resolution MFL data deliver, and what is the smallest defect what we could actually find? So first of all, with ultra-high resolution MFL data, we guarantee high data quality, which by far exceeds conventional MFL or eddy current scanners. It is able to detect indications from 2 mm in diameter and 10% metal loss, and is able to reach a sizing accuracy of ±4% under ideal conditions. The high level of automation guarantees also fast turnaround time, because no features or only a limited amount of features have to be followed up, but the majority of the work is meanwhile done by algorithms which are supported by AI and machine learning approaches. Actually, coatings up to 6 mm can be scanned and inspected with this technology without the need for removal. So let's have a look how extending inspection intervals is possible by this best-in-class technology and sensitivity. Let's assume we have a tank that is pretty new and which is commonly inspected after 10 years after commissioning. Normally, there's only very limited corrosion present at this time, and the next inspection date derived from the data does often not reach allowable limits given by the regulator. So in the end, it's extremely low detection threshold, and the repair threshold are needed in order to actually achieve what the code is offering us. So let's have a look at a floor scanner B. So the tank, let's assume it was constructed in 2010. Inspected in 2020, wall thickness was 6 mm in this case, and a detection threshold of 20% was used. So this leads to a calculated next inspection date of 10 years. If we look at the T-Bit Ultra that utilizes the ultra-high resolution and is able to detect from 10%, we only changed this parameter. So we left all the parameters the same, but only changed the detection threshold from 20 to 10%. The next inspection date calculation ends up with 25 years. However, the API maximizes this to 20 years. Nevertheless, we could reach double next inspection date from 10 years to 20 years just by changing the detection threshold from 20 to 10%. However, I mean, here you saw already which benefit ultra-high resolution data can deliver. However, this comes also along with some challenges. And in the next chapter, I would like to talk a little bit more about the complexities that come along and that have to be solved while using high-resolution MFL technology. So first of all, the ultra-high resolution stands for a higher sensor density. So on traditional MFL tools, we typically use 154 channels, but on an ultra tool, we meanwhile use more than 1,000 channels. So the resolution is around 7 times higher than before. And you can see that in the pictures already. So just by the higher resolution, a much sharper picture about any defect in the bottom plate can be drawn. However, with the lower detection threshold, we come also closer to the noise level. And this leads to an also increased number of false calls. Here on the left side, you can again see a traditional scan with a traditional MFL resolution. Here you can see this, clearly see the sensor lines, and you can see the defects that are boxed. On the left side is just a handful, but if we switch to the right side where we have the data set with the ultra high resolution, you can immediately see that we pick up a lot more indications. But parts of it are of course also false calls. And you can imagine that disabling these manually is almost impossible. So let's have a look at a comparison. So here we have a tank scanned in 2019 and with a traditional MFL resolution. Actually, this scan ended up with around 15,000 indications, whereas the same tank was scanned in 2024 with the ultra high resolutions tool, and we ended up with around 400,000 indications. Of course, a couple of these indications, these additional indications, can be explained by corrosion growth, but the majority, of course, is detected in the 10 to 20% range. And this is, of course, the add-on from the ultra service. So what are typical false calls that we look at in these data? So one typical examples are tack welds. So these tack welds are typical leftovers from the construction. This is additional metal that's originated from the welding process, so it's typically located close to a weld. These indications have a typical shape in the data, and on the right side you see three views. So on one side you have the plate view, then you have a C-scan and a line view. And all of these views are used for data evaluation and also assessed by our algorithms to identify potential false calls. Actually here, it's a pretty nice example because the shape of these tack welds is similar to an M. We typically call it the McDonald's M, and it can be easily identified by the algorithms and also disabled automatically. Another false call example are settlements. You can imagine that the tank is not always 100% flat. So therefore, to the unevenness of the plates, certain liftoff is created, and this is what you can also see in the data. So settlement indication usually appear as a straight line that runs along the width of the line plot and also has a typical shape different to a normal corrosion indication. So therefore, our algorithms are also trained to identify these automatically and also, of course, disable them. So as mentioned earlier already, so the increased number of channels, the increased sensitivity leads to much higher amount of indications. What we found out over the last couple of years is that about 50% of all indications are in the range of 10 to 20% metal loss. However, 5% of these are only real. And the challenge here is to identify the false calls, disable them, and of course also keep the true calls in. So therefore, I would like to talk a little bit about the so-called confusion matrix, as we can have different versions of true calls and false calls. Actually, we can have the true positive calls, which is actually a corrosion location, so where we have real corrosion, and where the software and the tool identified also an indication, and therewith we have a true positive call, so a match. Then we can have the true negative features, so that's where no corrosion is present, but the software and the algorithm also identified nothing, which is then also good. But then we have the false positive and the false negatives, where the false positives are the so-called false calls. So that's a location where the software and the algorithm called an indication, but there was actually no corrosion present. And this, of course, needs to be filtered out. And then we have the false negatives, which are, of course, the worst of all the indications, because these are the ones which the indications where there was nothing identified by a software. However, there was something present. And these we, of course, also these indications we try to minimize. So in this overview, we see the blue box represents all potential detection boxes. The red circle represents all indications called by the software, and the green circle represents all real indications. So the overlap between the red and the green circle are obviously the true positives, so where there's a match between real corrosion and what software identified as corrosion. This area we, of course, want to maximize. However, there's some remaining false positives, the so-called false calls, which are represented here by the red, and some false negatives that are not detected, which we, of course, like to minimize. I would like to make a note here. So when we talk about the POD, so probability of detection, it is easy to improve the POD just by increasing A, so the boxes that you identify as an indication. However, all of these indications that are detected and boxed also need to be assessed from a data evaluation perspective. So the workload is proportional to the size of this group. And there the question is there a trade-off? So this leads actually to our solution. So as you can imagine, a high amount of indication cannot all evaluated manually. And that's where the automation based on AI and machine learning comes into play. And here I would like to pull up again the example that I had before. So the tank that we've seen before was actually a 60-meter diameter tank. The inspection data gathering was done in 3 days, independent which tool was used at the time. And the defects found in the standard mode was about 15,000, whereas in the extended or ultra mode were 400,000. Actually, the data evaluation time was 0 seconds because data is evaluated on the fly. You immediately, while driving over the defect, get length, width, and depth information, and also if a defect is on the top side or on the bottom side. If you look at other systems in the market that work in detection mode only, and if we use just the first example with the 15,000 indication, if every of these indication has to be followed up by a traditional method like QT or pit gauge or whatsoever, and we calculate 3 minutes per follow-up, we would end up with 750 hours of additional effort, which is about 75 man days. So we all know that this is not done, but what is if this is not done? And it is a risk in the end that remains. Therefore, we have developed a solution, and actually our solution is a 2-staged approach. So we combined the automatic data evaluation with also a certain portion of manual data evaluation. However, the first step of the data evaluation is done by our algorithms. This is very fast, with a reproducible quality, with a reduction of the human effort, and also to a certain extent can cope with unusual data. So I put an example here for an example database that can of course differ if you have different databases. But what we typically reach is if we have 100% of indication inside a tank, the algorithm typically handles 85%. So 85% of the false calls are typically taken out by the computer. In this case, there were 12% of true indications, which of course were rightfully kept in. So there was a remaining effort of 3% here to be done by the evaluator. And there, in the programming of the algorithms, we also made sure that especially on the deep indications, also the operator has to look over it. Of course, we let the algorithm run also over the data, but especially for deep indications, we want to have like a 4-eye principle and also let a human look over it. So how is our algorithms or our algorithms set up? So actually over the last decades, we collected quite some tank bottom inspection data with our T-bit, but also with our T-bit Ultra. In each and every inspection, we do also certain kind of follow-ups just to do random checks if the tool is performing as we want it to perform. So this is only a few indications that per inspections have to be followed up. But we use this as ground truth data to feed into a database and base our algorithms on. If we now have a new feature that comes in during an inspection, it goes through these algorithms, and first of all, we have to identify, is it a double feature and a true call or a false call? Because we also have double features in our data set as we drive also stripes with certain overlaps. This has to do with the tool design as the magnetization of the tool decreases to the side of the tool, and with driving a certain overlap, we just make sure that we cover these areas twice and just assess the data properly. However, a double feature is also a true call, and in the first place, we have to identify the true from the false calls. After that, we look at the true calls and the double features, and with applying certain rules, we keep each feature in only once and take out the double ones so that the true calls remain in, and only once, of course. The false calls are then even further assessed as we look at certain classes. So two of these classes I showed you before. We can have tech wells, we can have settlement indications, but also we can have other indications which we classify as false cause. And these are classified then in 5 different classes, which we in the end can also assess and look at if we want to. So this regarding our algorithms, and I would like to now talk a little bit more about the performance of the tool and how we validated it over the last couple of years. So the first stage of tool validation we actually performed in-house. So therefore we produced plates in different thicknesses, 6, 8, 10, 12, 15 millimeter, and we simulated coating up to 6 millimeter with different plexiglass thicknesses. Actually, we put in defects on the top side and the bottom side of the plates to check the performance for these different types of feature classes, and the defects with a huge variety of dimensions have been put in. So we start from 1 millimeter in diameter, a millimeter in diameter up to 60 millimeter and a depth of 10 to 100%. And actually we put in all API conform defect shapes. In the past, performance was often validated on just flat bottom holes, but we thought let's get to a more realistic feature shape and let's use ball shape or hemispherical defects. These bunch of plates have been scanned with several tools by several operators. So in total, more than 20,000 indications have been assessed to prove the tool performance. And on the right side, you see where we ended up with. So actually, the T-Bit Ultra can detect indications from 10% metal loss and 2 millimeter in diameter. We can reach sizing accuracy of plus minus 4%. Coating thickness possible up to 6 millimeter for automatic sizing and 10 millimeter for detection only. Plate thickness up to 60 millimeter. So the number of channels I mentioned before, more than 1,000. Internal, external discrimination is possible, and the scan speed up to 1.2 meter per second. All these results flow into a detailed validation report where we have dedicated BOD curves per wall thickness and also sizing accuracy tables per feature class. And actually, when we did this exercise, we were looking for a definition of feature classes, and there was nothing available in the tank inspection business. So therefore, we looked a little bit aside and found something on the ILI side, and we used actually the POF from the Pipeline Operator Forum. You can, of course, argue it's from the pipeline side, but we rather like to have a standard than just defining the standard ourselves. I can tell you that at the moment, there's discussion ongoing on the API side as well to come to such a definition also for the tank inspection business, but this is not yet defined, and unless that is the case, we thought let's use this. What we actually did is we grouped the indication in different classes from pinhole, pitting, and general corrosion. What we defined as per POF as a pinhole is defects up to 10 millimeter in diameter. Pitting is something from 10 to 30 millimeter in diameter, and general corrosion from 30 and above. And here an example on a 6 millimeter plate, uncoated situation, we can reach this sizing accuracies for the depth sizing. And as you can see, there's of course difference per feature classes and differences per wall thickness and lift-off combination, but that's why we put all this information into a detailed validation report where it can be derived from. However, we said only doing the validation on artificial defects is not really realistic. So therefore, we also said, let's have a look at a couple of data sets, real data sets, and let's assess how good the quality and the performance of our tool is also under these conditions. Therefore, we looked at more than 50 inspection data sets, and these tanks had a huge variety in plate thicknesses, coating thicknesses, surface roughness, and cleanliness. And actually, we compared the T-bit readings with ground truth data of more than 1,800 indications. The ground truth reading actually were mainly pit gauge measurement for internal indications, but also some 3D laser measurements, and UT measurements for external defects. And what you can see on the bottom left is the results of the performance that we assessed. Of course, on different tanks, we did different amounts of feature verification, and you can see the sizing accuracy also differs per tank. However, as mentioned before, under ideal circumstances, we reached accuracies of less than 5%. Under certain circumstances, sizing accuracy is a little bit worse. However, in average, we reached an accuracy of 10 to 12% over the whole range of tank bottoms. However, we also said this is still not sufficient, because this was all done in-house by ourselves. And we said it would be good to have a third party looking over our tools and processes and procedures. And that's why we asked the TÜV Nord to also assess our performance according to the INIC guideline VGB R516 second edition. And this has happened in 2021. And there a guy witnessed a couple of tests and actually granted the certificate that our TBIT and the belonging procedures and personnel can hold what we specify. So let's summarize. What are the benefits of ultra high resolution MFL data? First of all, the sensitivity. So with the highest sensitivity sensor spacing of 1.6 millimeter, we can very early detect corrosion defects from 10% and 2 millimeter in diameter. We have a huge confidence in the data because MFL is used since more than 40 years in the industry. And meanwhile, we have a very reliable data analysis, also supported by certain algorithms and also validated to a huge extent. We have a reduction in hours in confined space due to the high level of automation, which is first of all good for the personnel, but secondly also assures fast turnaround time for the asset owner. All these results can be used for RBI, which support the optimization of inspection interval calculation and next inspection date determination. And last but not least, also this high accurate data enables also the AI and machine learning. And this will, of course, progress in the future that we pretty soon probably come to also AI-powered predictions. So the TBIT Ultra actually combines a lot of these parameters. Actually, it inherits the high-resolution MFL sensors. The software is automated to a high extent. We have a 360-degree steering to scan along the tank shell to minimize the blind zones there. We have the possibility to operate in remote control when there's a heating coils present. We actually have also a little brother of the TBIT, so-called blind zone scanner, which can be used to use also the areas where the TBIT is too big for, to cover as much as possible of the surface of a tank. And in the end, all of that guarantees less out of service time of your asset. And I would like to close my presentation here with a statement from Seth Stevens-Davidowitz, who said, the big data revolution is less about collecting more and more data. It's about collecting the right data. And that's certainly true. I mean, it doesn't make sense to just collect more data with additional challenge. You also have to derive more information out of it. And that's what we are currently or every day working on to improve this. So thank you very much for your attention. And I'm, of course, happy to take any questions.
Thank you very much, Richard. Very, very nice summary of what you can get to with AI and machine learning. It's very impressive, the wealth of data, but particularly how you can deal with that and analyze that using the true and false call analysis as well. And I was also interested to see the benefits from a safety perspective as well in terms of reduced time and confined space. So Ikesh, we've got plenty of time for questions. Ikesh, would you like to give the first question? I'll then open just the microphones for the audience as well, so they have the option of either asking directly or going from the chat. Okay, thanks, Ikesh.
Thank you, Martin, and thank you, Richard. Excellent presentation and overview of MFL TBIT, combining AI ML capability. Echoing what Martin already mentioned. In addition to that, I like your initial slide on how you presented the evaluation of MFL from 90s till what is the current status. Also, very impressive sample size that you have done for your internal validation as well. So very well done on that. The question I have is, and that's a bit of concern for me as an end user. On slide 18, you presented an overview of the standard MFL comparing with the TBIT. And if I read it correctly, with the latest version of TBIT, there are many more defects that you found in the 100% or higher wall loss category, which was not at all detected with standard MFL. So can you elaborate a bit more on that?
Of course. I mean, a few of them may have, of these additional defects, may have grown over time. I mean, there's a time of 5 years between these two inspections, and there was certainly corrosion growth present. That is one explanation. The next explanation is, of course, the higher sensitivity that we apply. So I mentioned that in one of the former slides. In the past, we had around 154 channels on the tool, also on the T-bit. And there we had a sensor spacing of around 7 millimeter between two adjacent sensors. And with the ultra high resolution, we get to a sensor spacing of 1.6 millimeter. So we are able to detect many more smaller indications, but also they can be deeper, so smaller in diameter, I mean. And of course, with the implementation of the ultra high resolution, we also look meanwhile at other room directions. So we have 3-dimensional hole elements on the tool. And in the past, we used the horizontal holes mainly. And nowadays, we use also vertical holes and transverse hole elements in the data evaluation process. And last but not least, internal-external discrimination has been improved over time, which is the first step in the sizing that has to be all right. Because if you look at a signal amplitude from the same size defect, but on the top or the bottom size, the amplitude is much different. So therefore, you have to make sure that you assess the feature classification, if it's on the top or the bottom side, right, in the first place, to get also to a proper feature sizing. So also by increased accuracy, we reach here more indications in the higher level as we had before.
Okay, very well explained, Richard. Thank you. Martin, back to you for other questions.
Yes, certainly. So I've some issue with my camera at the moment. I'll get that resolved. I've opened the microphones up to the audience. So if you have posed a question in the chat and you want to ask directly, then feel free to jump in. The first question I have is from Rusian Teremblahov. Are the cleaning requirements for the tank floor different when performing standard MFL compared to ultra high resolution MFL?
Actually not, no. I mean, we have certain cleanliness requirements and we have them documented also in a certain procedure or in a certain document. So there's certain things that need to be considered. Of course, the bottom should be free of dust and moisture. And typically bottoms are high water pressure cleaned. And there's also certain standards that you can apply for a cleanliness. But to answer your question, actually, there's no difference in cleanliness requirement between a standard and ultra service. No.
Okay, perfect. The second question from Yogas Pimpale. How does the high resolution MFL behave with coating and difference in thickness?
That's a good question. Actually, with the implementation of the ultra high resolution, we thought also that we give the coating thickness and the lift off that it generates more attention. That's why we also implemented the coating thickness represented by plexiglass plates in the calibration process. So during our annual tool calibration, we run the tool over all plate thicknesses, but also over all lift off thicknesses. And that leads to very accurate calibration curves. So we measure the lift-off inside the tank continuously with eddy current sensors. And this value is immediately considered in the MFL sizing on the feature depth, length, and width. So therefore, lift-off plays a role also from a performance perspective, but we calibrate our tools on this lift-off and we consider lift-off values, lift-off measurements on the fly in the MFL sizing process.
Okay, great. Thanks, Richard. The next question from Paul Harbers. MFL and tank bottom glass fiber coating are not best friends. Does ultra high resolution and AIML help you get better results through glass fiber coating? I think you may have just answered that, but that's the question.
I mean, in the end, from a coating perspective, we have to make sure that it's non-magnetic and non-metallic, as it will otherwise influence the MFL reading. However, as I explained in the other question before, is with the ultra high resolution MFL, we paid more attention in the lift off correction that is generated by this glass fiber reinforced coating. And therefore, I would say the performance improved significantly comparing standard MFL to ultra high resolution MFL when looking at coated tank inspections.
I recall many years earlier in the development of the tank floor scanners, one of the issues of concern was the quality of the steel and the noise level you got. How are the results and how is the sort of automated analysis affected by either noise levels or by the sort of condition of the surface condition of the steel in the tank that you're inspecting?
Yeah, there's definitely an influence, and I have to say we're also still learning there. But with the ultra high resolution, as mentioned in the beginning of the presentation, we're coming closer to the noise level. So the reduction of the detection threshold from 20 to 10% leads us more, or gets us very close to the noise level. And I would lie if I would say this does not have an influence on the data. So therefore, it is very important there that the algorithm is properly trained and programmed to filter out all this small stuff, so to say. And in one of my slides, I also mentioned that 50% of all indication are in the range of 10 to 20%, but only 5% is real. And it is the challenge is, or the target is, of course, to filter these 5% out properly, because we don't want to know about all this false course. We want to know about the real stuff. And yeah, we are still every day trying to improve our algorithms and train the algorithms further with additional data. But I think we have made quite a step there already with the existing ultra data that we gathered over the last 3 to 4 years.
Yes, I mean, it's very impressive, particularly the way you can gather so much data, but the AI machine learning is then enabling you to make use of that data through the analysis. Another question from Rennie Goddery. Is there a remote controlled version available which could eliminate tank entry?
So actually, it's not a complete remote controlled version. I mean, we have a version where each and every T-bit can be used in remote control, but still we have a data cable connected to the laptop. So we can disassemble the steering arm, and with a control unit, we can steer the tool, so drive it over the plates. But there's still a cable attached to the laptop to assure proper data transfer. So we cannot steer the tool from the outside of the tank, so there's still the need for the operator to be inside the tank. But with this, we enable the tool to move under obstacles like heating coils. We need a minimum clearance of 250 millimeter, but that is possible in remote, but not completely steering from the outside is not completely possible.
Great, thanks, Richard. Next question from Michael Sim. How does moisture affect the data?
Moisture shell itself doesn't really have an influence on the data itself. Typically when there's moisture, there's also accumulated rust at these areas. And this could potentially have an influence of the data. I mean, with the tool itself, we can run through some water. So the sensors itself and the drive units, that is all watertight, that is no problem. However, if there would be a complete flooded ground, we would of course not like to do this. I mean, this is defined in the cleanliness requirements. But in the end, moisture does not have a direct influence on the MFL and eddy current measurements. And if it's not too much, we can also still do the inspections through small areas of water.
Richard, if I'm correct, the MFL, it can separately detect top surface and bottom surface defects. Is that correct? And if so, can you analyze the two sets of defects differently? Yes,
exactly. So it is definitely possible to do internal and external discrimination, and this with the new technology also with a high certainty of more than 95% correctness. Actually, it is the internal and external discrimination, as I explained before, also is a very important point for the accuracy in the depth sizing as well. It's not only important to, in the end, define the proper repair method, because of course internal indications are differently repaired than others. So therefore operators want to know if the defect is on the top or on the bottom side. It also plays a crucial role for the depth sizing, because there's an amplitude of the same size on the top side has a different amplitude to the same defect on the bottom side. And therefore the discrimination is a crucial factor in the performance, also on the feature depths, but also length and width sizing.
Okay, you mentioned an API initiative on feature classes and classification. Are you able to say a little more about that, and also if there's been a similar discussion in, for example, in the EMEA 159 standards body?
Yeah, so I cannot tell you a lot of details there, because there are other colleagues are involved which are participating the committee meetings. However, there's discussions ongoing on exactly that topic, that they identified that we haven't really defined different feature classes in other parts of the industry, like the ILI business, that is available for a long time already. And especially on the performance side, it is helpful to have a certain standard that you can also compare performances of different inspection methods and tools. So therefore, discussions are ongoing. They, as far as I understood, the values will differ a bit from the POF. So pinholes will be probably not defined as 10 millimeter defects, but probably smaller than that. But there's nothing finally agreed yet, and I also don't have many details. I just know that this discussion is ongoing.
Okay, perfect. Thank you, Richard.